Okay, so tonight we're going over what's called the impulse-momentum theorem. Now I want you to know that I taught impulse to you the way that I did because I wanted you to see a connection between work and impulse. And if you remember when we started this unit, I taught you work, and then I taught you kinetic energy because work is a change in kinetic energy. And so I wanted to teach impulse and momentum in the same order because impulse is a change in momentum, the thing you're going to learn about tonight. Now, because I chose to teach impulse in this order before I taught you momentum, which again I think was a good idea to help with the connection between impulse is over time in the same way that work is over a distance. So work is force times distance, impulse is force times time. And I really want you to see the connection between those two things. One happens over a distance, one happens over time. But because I taught them in that order, we're now going to have to slightly adjust our definition of impulse. So impulse, I told you before, is force over a time, which is a correct statement. But now we're going to clarify that a little bit, and you'll see the clarity as we go through tonight. We're going to adjust this definition to impulse, which is a vector, is force, which is a vector. But it's not just force, it's the average force. So the average force applied over a time. Which comes back to the question that several people asked of if you have a force-time graph and you get some kind of force-time graph that looks like this. You are asking me, let's say this is 3 seconds, and the question says, what's the impulse over the first 3 seconds? Lots of people are saying, well, why don't I just take the force at that time and multiply, if this force is 5 newtons, why don't I just do 5 times 3? Why do I have to find the area under the curve? Well, the answer, the better answer to your question now, is that impulse works for an average force, not just for a force at a specific time. So it's the average force over that whole time. So if you applied 1 newton the first second, 2 newtons the second, and 3 newtons the third second, 1 plus 2 plus 3 newtons, and to take the average, you do it over its total time, you'd find that your average force wasn't 3 newtons. If you do that math, your average force is 2 newtons. So anyway, the answer to the question of why were we not just multiplying the force and the time, impulse only works for an average force, or the impulse equation only works for an average force. And anytime you have a non-constant force, so the average is not the same as the force at any time, you have to find the area whenever you have a non-constant force. And that's the reason you couldn't just use the equation and multiply whatever the F was times whatever the T was, because it wasn't the average force. Okay, well now that you've got that, let's think back to, so I promise that connection, why I did that will become clear in a bit. Let's think back to Newton's second law, which said F net equals mass times acceleration, where force and acceleration are, of course, vectors. We're going to worry about vectors a lot tonight. This is not actually the way that Isaac Newton, so the person in this picture here, Isaac Newton came up with Newton's laws of motion, the second law being one of them, Newton's second law of motion. He actually did not write his second law like this. This is the way that physicists write it now. The original way that Isaac Newton wrote the second law was F net equals change in momentum, and we're going to use P for momentum, change in momentum over change in time. Now, and just like when I derived the work kinetic energy theorem, you're going to have to bear with me for some math, and then you'll see where it's going at the end. So now let's talk exactly what is change in momentum. So let's rewrite that. Change in momentum is a final momentum minus an initial momentum. And those little harpoons, remember, mean vectors. And now we can write momentum as what we know it is, m times v. So final mass times final velocity minus initial mass times initial velocity. Now, most objects that we deal with are going to have the same mass throughout. Objects' masses generally don't suddenly change. So if we say that these masses are the same, if we say mf is the same as mi, then we can factor out these two masses and rewrite change in momentum as m times vf minus vi. And remember, I'm just noting what things are vectors with the harpoons. And now we can rewrite that more simply. Change in momentum is mass times change in velocity. Now, if we take this statement here, change in momentum is mass times change in velocity, and put it back into Newton's second law, we're going to start to see some interesting things. So I'm going to do that on the next slide just to clean up a little bit. Okay, so now let's take these two equations we've just developed and put them together. F net equals m delta v over delta t. Now if I multiply by delta t, this equation should look really familiar. So F net times delta t equals m delta v. A force over a time is an impulse. So impulse is m delta v. And as you've learned, m delta v is a change in momentum. So impulse, therefore, big conclusion, is a change in momentum. So that's a big takeaway here. Impulse is a change in momentum. Another big takeaway I want you to get is if we write this out a little differently. So we just said impulse is change in momentum. Impulse equals change in momentum. I also told you earlier that impulse is average force times time, and still equals change in momentum. So we can expand this back out because this equation is most useful in the expanded form. Average force times time equals mass times final velocity minus initial velocity. So anytime you have a question that gives you an average force and wants to know something like final velocity or, oh, that's a vector too, or initial velocity, this is the equation to use. And this equation is the impulse momentum theorem. And if we write it out one more time, just pointing out that impulse is equal to what we've written, this connects all three units we've had so far. So impulse is average force, which is a unit 2 thing with Newton's laws. Average force times time equals mass times change in velocity, which is a unit 1 kinematics thing. So here we have a statement that connects all three units and is really useful. Impulse from unit 3 is average force, unit 2, times time, which is also equal to mass times your change in velocity. So this equation can be really useful in a lot of situations because it connects a whole bunch of different ideas. So if you're given an impulse and asked to find something like an average force, you can use this equation to do it. If you're given an average force and asked to find a mass, or a final or initial velocity, you could use this equation to do it. So this impulse momentum theorem is something that you should know, should understand, and should memorize. So maybe take a little bit, copy down that equation, know that it's called the impulse momentum theorem, and memorize it. Impulse is average velocity times time is mass times change in velocity. And that's the big takeaway from this first video, that statement right there.